Hello everyone, this is Jansi. Me and Anish have worked on this research project from last December. And that is human activity and vital sign recognition using ultraviolet radar sensor. So essentially, this is the radar module that we worked on, and these are the two antennas. One is for transmitting the electromagnetic pulses, and the other is for receiving the electromagnetic pulse. Um, First, we worked on extracting the radar signatures of human activities. Mainly, there are four activities. That is one, walking away in towards the radar, sitting down, standing up, and then falling action. So this is the pipeline of the signal processing. First, we collect the uh, data, motion data, and then we arrange it into a matrix that is known as range time matrix. Each row corresponds to each scan, and each column corresponds to the fast time index. And then this matrix is then uh, fed through a motion filters. Namely, we worked on four motion filters. Those are second order difference filter, FIR4, FIR2, and then IR2. We'll tell you which one worked best for us. And then the data is passed through envelope detection to isolate the motion intensity. Then static background removal. In this process, um, when the electromagnetic signal is also reflected by the static background objects. So we want to remove those reflections. Uh, by doing so, we can isolate motion more effectively. Range bias compensation is to accurately depict the range. So first, let me show you the demo of how it works. So this is the TDSR monostatic radar module UI. So here I'm starting the scan. Actually, this is the received radar signal, the one in blue, that is raw received radar signal, and the one in black is the motion filtered signal. Here I am, walking away from the radar, and then coming back. As you can see, the radar is detecting the motion that I'm walking. So this is how the radar logs the information. Here, this 480 is the fast time indices, and these are all the scans. This is the signal intensity values. Next, let's plot this. So I've already plotted the data. If you directly plot the data in Excel sheet, this is what you'll get. So this is not very useful for us in terms of detecting where the motion is. So first we'll apply motion filter to separate the motion. As you can see, we can see a little bit, but it's not very um, dominant. Next, we'll apply envelope detection. As you can see, wherever the motion is happening, the intensity is more and motion is effectively isolated. But this is not very clear. As you can see here, there are background reflections, and then we apply background removal. Now it is much more clear. Um, how do you interpret this? So first, I'm near the radar, so here I am, and then and I'm moving farther away. As scan pass by, I'm moving this radar signature is moving away, and then I'm coming back towards the radar, and this is like this. This is you can you might want like to imagine it should be like a straight line, but there is an effect called ghosting effectively. So if you are near the radar, you would get signals all over here. So so this is quite common in radars. Next, we'll see the filters. As I've discussed here earlier, we worked on these four filters. So this is the output of FR2, FR4, IR2, and the second order difference filter. As you can see, there are some disturbances. The background is not, it is detecting unwanted motions also. The second order difference filter um, isolated the motion more effectively than the others. Next, let's discuss about the second part of our project, that is respiration measurement. So here is our human subject, and this is our radar. We would scan the radar for like 600 scans. Now, whenever the radar pulse transmits, it would be reflected by the motion of the lung, and we've depicted uh, using this formula. So, uh, let's say d naught is the distance between the radar antenna and the chest, and we've depicted it using this formula. Next, what we've done is that we've passed each signal to a fourth order Butterworth IR filter, which has a passband frequency of 0.1 to 0.5 Hz, which corresponds to a breathing rate of 6 to 30 beats per minute, which is aligns with the physiological range of human breathing. And to isolate only the breathing signals from high frequency signals, such as heartbeat and so on. And then we calculate the power spectrum of each signal, and then we rank this power spectrum into uh, bins, essentially. This is the FF, after taking FFT and calculating the power spectrum. We got multiple peaks here. So we take the peak with highest one, and then calculate the BPM like this. And then we multiply it with 60 and calculate the BPM. But taking only one peak might not be accurate. The breathing may not be regular. Sometimes there may be irregular breathing. Sorry. So it's better to take top 1, 3, 5, or 10 pins. So let us see an example here. So this is the GitHub repository by our team. I'm taking this example. So the manual calculated breathing rate is 14, and let's see what we get. So our estimated breathing rate is 12.5, around 12 and 13, which is not bad. One or two maybe. Fine. Um, so these are our results for the breathing rate. As you can see, we have two subjects and three trials for each, which accounted for slow breathing and irregular breathing, casual breathing, and these are our results. For one case, the results are not very accurate. That is when the breathing is not regular. So we are still currently working on our approach in including irregular breathing also. And we're also working on recognizing human activity signatures using AI, so ML. So these are human signatures. This is walking, sitting down, standing, and coming towards and falling down. As you can see, it is very difficult to differentiate between sitting down and standing up action. So we are actually working on developing an ML model to detect those things. So that's it for our projects. Thank you for listening.